This is a photograph of Teton Dam taken on the morning of June 5, 1976. Look at the right side. That plume is the reservoir leaving through the dam. 305 feet of earth. 11 people dead. $400 million in damage. I'm Ray Callahan. This is not the story of a dam that broke. Every earth dam leaks. This one failed because nobody could take the water back out. The drain was still under construction the day they started filling. And the federal auditor wrote down why they filled it anyway. Here is the sentence this investigation runs on, and it is not mine. It comes from the Comptroller General of the United States. Report CED 77-85, page 46. Quote, apparently, the decision to begin filling the reservoir and to continue filling it without the availability of the main river outlet drain was made to avoid the possibility of incurring contractor claims. End quote. That is a federal auditor stating that the Bureau of Reclamation filled a dam it had no way to empty to avoid a contract dispute. You have probably heard a different version, that they filled it too fast, and the speed is what broke it. The panel that investigated this failure says that is not correct. In writing. Conclusion 6. The real finding is worse. Here is what I am going to prove over the next 20 minutes. First, that this dam was built with no second line of defense against leakage its own designers called inevitable. Second, that the one defense it had left, lowering the reservoir, was traded away in writing, twice, for a construction schedule. Third, that on the morning of June 5th, a man was sent into that drain to open it and could not. Who decided that, and why? That is the question this story usually stops at. It has an answer. The answer has a page number. Teton Dam was authorized on September 7, 1964, under Public Law 88-583. It was the centerpiece of the Teton Basin project, flood control, hydroelectric power, and supplemental irrigation for eastern Idaho farmland. The construction contract was awarded in December of 1971. Work started that February. The finished structure was a central core-zoned earth-fill dam, 305 feet above the valley floor. 405 feet above the lowest point in its foundation. The crest sat at elevation 5,332 and ran 3,100 feet across the canyon. 10 million cubic yards of compacted earth. Behind it, a reservoir of 288,000 acre-feet, 17 miles long. Topped out November 26, 1975. Now the ground it stood on. The Teton River runs through a steep-walled canyon cut into rhyolitic ash flow tuff. Hard volcanic rock thrown out by eruptions long extinct. The independent panel's third conclusion describes it in one sentence. The volcanic rocks at the Teton Dam site are highly permeable and moderately to intensely jointed, and water was therefore free to move with almost equal ease in most directions. Not porous like a sponge, jointed like a stack of broken plates, open cracks running in every direction right through the abutments the dam had to seal against. And this was not a surprise. Conclusion number 1 of that same panel. The pilot grouting program carried out in 1969 forecast the difficulties to be experienced in construction of the final grout curtain. 7 years before the failure, a test program told them what the grouting was going to be like. Then there is what they built the dam out of. Eastern Idaho is covered in wind-deposited silt. Loess. Fine, uniform, easy to compact, locally abundant. So it went into the impervious core and into the key trench. The panel's fourth conclusion. Those clayey silts are highly erodible, and their use adjacent to the heavily jointed rock of the abutment was a major factor contributing to the failure. So, cracked rock and a core made of material that washes away. The seepage control had 2 parts. A key trench. A deep slot cut into the abutment rock and backfilled with that same silt to force water to travel farther. And beneath it, a grout curtain. Cement pumped under pressure into the joints to seal the rock. The grouting did not go well. This is the Bureau of Reclamation's own account of its own project. Workers pumped in over twice the budgeted amount of grout, but the fissures, especially those near elevation 5,200, continued to absorb the material. Eventually, grouting stopped because of cost overruns, leaving some fractures partially sealed. Remember that number, elevation 5,200. It comes back twice, and the second time, a man will be standing in front of it. But here is the part that matters more than the grout. Every earth dam leaks. Reclamation knew that. Their own design documents assumed it. So what was supposed to catch the water that got through? Nothing was. And that is the actual root cause of Teton Dam. Let me show you what should have been there. The mechanism that destroyed this dam is called piping. Not a crack, not a collapse. Erosion from the inside, along a path you cannot see. Water finds a route through or under the core, and because the core here was fine, wind-blown silt, the moving water picks up grains and carries them out. Removing grains widens the channel. A wider channel moves more water. More water removes more grains. Once it starts, it accelerates, and it accelerates where nobody can look. Think of a garden hose lying in loose soil. Nothing happens for a long time. Then a small channel forms, and within minutes you have a trench. The dam version is 6 feet across. The defense against piping is not a better seal. It is a filter. In modern practice, you assume the water is coming, and you build a graded layer of sand and gravel downstream of the core, coarse enough to let water pass freely, fine enough that soil particles cannot pass with it. Water drains away harmlessly. Soil stays home. You are not preventing seepage. You are making seepage boring. Teton Dam had no such protection. The panel says so in Conclusion 14, listing the design decisions that permitted the failure. Inadequate provisions for collection and safe discharge of seepage or leakage, which inevitably would occur through the foundation rock and cutoff systems. Inevitably would occur. That is the panel describing what the designers themselves expected. The leak was in the plan. The response to the leak was not. I want to be precise here, because this is where most accounts of Teton get it wrong. The grout curtain was not shoddy work. Conclusion 7 says the opposite. Great effort was devoted to constructing a grout curtain of high quality, and the resulting curtain was not inferior to many that have been considered acceptable on other projects. The crime was not the curtain. The crime was betting the dam on it. Same conclusion, final line. Too much was expected of the grout curtain, and the design should have provided measures to render the inevitable leakage harmless. A year later, the Department of the Interior investigated itself. The Teton Dam Failure Review Group reported in April of 1977, and it is blunter than the outside experts were. Page 87. At Teton Dam, a defensive design for adequate protection of the embankment core material was not provided, perhaps the single most important finding of the investigation. And in its conclusions, reliance on the grout curtain for total control of damaging seepage inhibited adoption of other design features that could have prevented the failure. Then the sentence the Bureau wrote about the Bureau. Quote, "The Bureau had the necessary information available to develop an adequate defensive design. A safe dam could have been built at the site utilizing design concepts that were known at that time. Nothing had to be invented. The knowledge existed. It was not used." One more detail, because it explains where the leak started. The key trench was cut with steep sides. Backfill a narrow slot with compacted earth, and the fill hangs on the walls instead of resting its weight on the bottom. Engineers call that arching. It reduces the stress at the base of the trench, and low stress in brittle soil means cracks. Conclusions 8 and 9 run the finite element analysis. Near stations 14 and 15, water pressure could have exceeded the confining stress plus the tensile strength of the fill. The water could split the soil open by pressure alone. So the failure path is this. Water moves through unsealed joints beneath the grout cap near station 14. It reaches a rottable fill with nothing protecting it. It cuts a tunnel across the base of the key trench. The tunnel finds the contact between the core and the abutment rock, follows it downstream, and comes out the far side of the dam in daylight, which leaves exactly one defense in the whole system. If the water starts moving, you take the pressure off. You lower the reservoir. So let's go look at the drains. Teton Dam was designed with two. A main river outlet works in the left bank, and a smaller auxiliary outlet works in the right bank. Combined design capacity, about 4,250 cubic feet per second. The auxiliary alone was rated at 850. The rules for using them were published in October of 1971 in a document called Design Considerations for Teton Dam. Quote, "Unless adverse performance develops, unrestricted filling rates will be permitted to elevation 5,200. Above elevation 5,200, initial filling should not exceed 1 foot per day." There is that number again. The elevation where the grouting stopped is also the elevation where the design says, from here up, go slow. And the same document, 4 years before the fact, states the dependency in plain English. Quote, "After May 1, 1976, the flow in the Teton River exceeds the maximum allowable release from the auxiliary outlet works of 850 cubic feet per second, and the capacity of the river outlet works is needed in order to control the rate of filling in the reservoir." Written in 1971. After May 1, 1976, you need the river outlet, or you do not control this reservoir.
Now here is the decision. It is on page 57 of the GAO report, and it is the earliest link in the chain, late in 1974 or early in 1975.
A decision was made to begin filling in October of 1975, instead of waiting until the main river outlet was complete in May of 1976. The project construction engineer told the auditors why. The contractor installing the turbines needed enough water by mid-May to complete his testing program, and the Bureau had issued specifications that in effect required him to test during May of 1976.
But if the design considerations were followed, the reservoir would be almost empty then.
Two documents from the same agency, contradicting each other. And the resolution, quote, the designers and he jointly agreed to begin filling early so that the turbines could be tested as scheduled in May, and possible claims from the contractor for late testing could be avoided.
Read that slowly. Rather than absorb a contract dispute over a testing date, they started storing water in a dam whose main drain did not exist yet.
On October 3, 1975, the river outlet works was closed, so its contractor could place second-stage concrete and install the gates, pipe, and metalwork. The auxiliary was opened only partially. From that day until the dam failed, every drop of water that left Teton Dam went out through the small one. The contractor's deadline for finishing the main outlet was April 30, 1976. He missed it. The GAO records the reason. The main river outlet was not completed as originally scheduled because the contractor had not received the regulating gate from the manufacturer. So Teton Dam started storing water with one working drain rated at 850 cubic feet per second.
Was that enough? The Bureau already knew. It had run this experiment 11 years earlier.
Fontenelle Dam sits on the Green River in Wyoming. In 1965, during first filling, it developed a very large leak in the right abutment. The GAO lays the two cases side by side. The foundations at both dam sites contained fractured, cracked rock with fissures and voids. The amounts of grout used at both were very large. At both, designers planned to fill very slowly, so that if leaks occurred, remedial action could be taken. At both, an unusually heavy snowpack produced a much faster filling rate. Neither dam had instrumentation to measure seepage inside the dam, and both leaked during first filling when the main outlet works were not available.
6 conditions, 6 matches, 1 difference.
Quote, the leak developed much slower at Fontenelle, and the Bureau was able to lower the reservoir before a failure occurred. And the reason they could, in the auditor's own words, the unusually large capacity of the main outlet. 17,000 cubic feet per second versus 3,400.
And at Teton, on the day it mattered, even that 3,400 was not available. Fontenelle still lost over 10,000 cubic yards of embankment before the leak was stopped. It survived because someone could open a valve. And then the Bureau did something that makes this episode what it is. It wrote the lesson down and published it.
400 at Teton. In a 1967 paper on the Fontenelle experience, the chief engineer of the Bureau concluded, quote, this difficulty occurred on first filling of the reservoir, which was unusually rapid due to extremely large inflows and the fact that the outlet works were not being used so that some repair work could be performed. This experience illustrates the need for slow, controlled filling of reservoirs where unfavorable foundation conditions are known to exist. Unusually rapid first filling. Outlet works out of service so work could be done on them. Unfavorable foundation. That is not a hypothetical dam.
That is Teton, described 9 years before Teton filled by the chief engineer of the agency that built it. Somebody wrote this down before it happened.
The GAO's own comment. By averting a disaster at Fontenelle, the Bureau had seemingly learned a valuable lesson regarding reservoir filling. Yet at Teton, over 10 years later, the lesson was not applied.
Now watch how the reservoir came up.
Snow surveys started in January of 1976 and came back heavy. At Pine Creek Pass, the May 1st snow water equivalent was 193% of average. At the State Line course, 233. On March 1st, the reservoir stood at elevation 5,164, rising 0.2 of a foot per day. 2 days later, the project construction engineer wrote to the Director of Design and Construction in Denver, asking permission to exceed the 1 foot per day rate. That memorandum is reprinted on page 10-11 of the panel report. It lists 5 reasons. Here are 3. Reason 1 was recreation, finishing the clearing contract so the reservoir could open to the public in the summer of 1977. Reason 3, quote, filling the reservoir would enable us to observe the effectiveness of the curtain grouting.
Stop there. They proposed to raise the water faster, in part, to find out whether the grout curtain was working.
The same curtain whose grouting had been stopped for cost overruns. The same curtain the panel would later say too much was expected of. And reason 5, quote, "We have in the past experienced flows considerably above that which we can release from the auxiliary outlet works during March and April. If we experience this again this year before the river outlet works is complete, we will not be able to maintain the recommended 1 foot per day filling rate."
That is the author of the memo stating in writing in March that he was about to lose control of the reservoir.
The approval came back on March 23rd. The director relaxed the rate to 2 feet per day. His basis, quote, "The preliminary reservoir filling curves indicate that the reservoir filling will exceed 1 foot per day with required releases only during the month of May, when the maximum daily increase will be approximately 2 feet. Approved on a forecast of 2 feet. Nobody ever revised that plan. April 8th. For the first time that spring, the reservoir rose more than a foot in a day. The auxiliary outlet was still at about a third of capacity. April 22nd. The reservoir reaches elevation 5,200, the line where slow filling was supposed to begin. April 30th. The contractor's deadline for the main river outlet passes. The regulating gate has not arrived. May 11th through June 5th. The 2-foot limit is exceeded every single day. 26 consecutive days, averaging 3 feet a day, peaking at 4.3 feet on May 18th. The auxiliary outlet is running above its rated capacity. May 14th. Reservoir at elevation 5,236.9. The project construction engineer sends a faxogram to Denver. Panel report, page 10-12. Quote, "We do not expect that painting of the tunnel liner downstream of the wheel-mounted gate will be completed before June 10, 1976. Further acceleration of the painting to enable earlier opening of the river outlet works is not feasible." And then, quote, "Should the need for any water release through the river outlet works become imperative before completion of the painting, the resultant interruption would involve claims by the contractor for delay and additional cleanup and sandblasting."
The drain was essentially built. There was a paint crew inside it. Opening it early would cost money.
Denver's answer is dated June 4th. The panel notes it was in the mails on the day of the failure. Quote, "We conclude that the river outlet works need not be used prior to completion of the painting, unless problems directly related to filling of the reservoir develop."
Problems developed the next morning, June 3rd.
2 small seeps appeared downstream of the toe, 40 and 60 gallons per minute, June 4th. Another seep, closer in, 20 gallons per minute. Sunset at 9:05. From 9:30 midnight until 7 a.m. on June 5th, there is nobody at the dam. No reclamation staff, no contractor staff. 7 a.m. slightly turbid water is coming out of the right abutment at elevation 5,200. 7:50. A survey crew spots muddy water at the toe. 8:30. That flow is 20 to 30 cubic feet per second. 9:20. 40 to 50. Between 9:30 and 10, the project construction engineer considers alerting the residents downstream. He decides an emergency is not imminent and that he does not want to cause a panic. 10 a.m. a new leak opens 15 feet from the abutment at elevation 5,200. 15 cubic feet per second, turbid. He described a tunnel 6 feet across, running 35 feet into the embankment. 10:40. 2 bulldozers start pushing rock into it. 10:43. The sheriffs of Fremont and Madison counties are called. Around 10:57, 1 hour before the failure, a member of the project staff is sent into the main river outlet to ready it for opening. It needed 6 to 8 hours. 11 a.m. a whirlpool forms in the reservoir. 11:30. Both bulldozers slide into the hole. The operators are pulled out. 11:55. The crest collapses. 11:57. The embankment breaches. The panel fixes that time to within half a minute. Peak outflow, early that afternoon, 2,300,000 cubic feet per second. By 6 that evening, the reservoir was essentially empty.
And here's the last line of the auditor's chronology, page 46.
When the evidence of erosion from the leak in the Teton Dam was discovered, the Bureau's staff at the project could not immediately open the main river outlet drain because another contractor was behind schedule in completing his work on this structure.
That is the answer. Not a mystery, not a judgment I am making for you. A federal audit with a page number.
Downstream, the flood left the canyon as a wall of water 50 to 75 feet high. Wilford, 8 miles down, lost 120 of its 154 homes. Sugar City took 15 feet. Rexburg took 6 to 8 feet in minutes. More than 180 square miles were inundated, 771 homes destroyed, 3,002 damaged, 16,650 head of livestock lost.
11 people died, 6 of them by drowning.
The record disagrees on that count, and I will say so. Reclamation, the GAO, and the Bureau's own study of the evacuation say 11.
The independent panel says 14 lives were associated directly or indirectly with the failure. Both are defensible. I use 11. Deaths caused by the flood itself. Damage estimates started near $1 billion. The panel's best estimate was $400 million.
The verdicts. Conclusion 5. The contractors are cleared. Construction conformed to the actual design in all significant aspects except scheduling. Conclusion 6. The faster filling did not materially cause the failure. Conclusion 7. Too much was expected of the grout curtain. The design is condemned. The designer was the owner. The GAO, page 47. With no way to open the main river outlet drain immediately when an emergency is recognized, we believe the Bureau took unnecessary safety risks and placed too much reliance on the adequacy of its design.
And on page 62, the sentence that turns this from an accident into a practice.
Bureau designers told the auditors that diversion outlets are not usually completed on many of their dams before water begins storing, because it is more economical to install them after filling starts. Consequently, no control over the reservoir is available for 4 to 6 months on many Bureau projects.
Teton was not the exception. Teton was the practice meeting a bad foundation.
Congress passed the Reclamation Safety of Dams Act in 1978, and Reclamation built a Dam Safety Division to examine the dams it already owned. And in testimony to Congress, the Director of Design and Construction admitted something the Bureau's own historians kept. Reclamation often stopped a project before construction started. It had never stopped one after construction began. Teton Dam was never rebuilt. The Bureau's own history of the project opens its conclusion with 9 words. The Teton Basin project never had chance to accomplish its intended goal. The panel's final summary is polite. Under difficult conditions that called for the best judgment and experience of the engineering profession, an unfortunate choice of design measures, together with less than conventional precautions, was taken.
Here is the plain version. On June 5, 1976, a man walked into the drain of Teton Dam to open it.
It was going to take him 6 to 8 hours because the painting was scheduled to finish on June 10th. The dam gave him 57 minutes.